This screencast is about section 3.1, Extrema on an interval. It's the start of our new chapter. Basically, in calculus, we spend the entire chapter devoting all of our time to determining the behavior of a function f on an interval I. What I mean by behavior is where is it increasing, where is it decreasing, does it have a max, does it have a min, all of those important features. We're also going to look at some other features later on in the chapter as well. Basically, what I'm going to show you is how you can actually use derivatives to answer some of those questions. The first thing we need is the extreme value theorem. It says if f is continuous on a closed interval, ab, then f has both a minimum and a maximum on the interval. What that means for you is it's guaranteeing both a maximum and minimum exist. Now, it's a little strange to think about. If I draw a parabola, you can clearly see where the minimum exists. But where's the maximum? This is where the whole part about a closed interval comes in, from A to B. We're only looking at designated sections of the curve, maybe from here to here. So starting at that location, all the way up there. So I'm going to remove part of this. Now let's look at the function again. It definitely has a minimum, but then its maximum that's being guaranteed by the extreme value theorem is right up here. It occurs at an endpoint. The only way that's going to happen is if we have that closed interval, so it's necessary, part of the theorem. So we have a minimum and a maximum guaranteed on every graph. Now let's take a look at different parts of a curve. I just want to give you some names for these different features. So here's just a random graph, f of x. I went ahead and labeled some important points on this graph. The starting point and the stopping point, A and B. We have some minimums, some maximums. Now here, these aren't the very highest points on the graph necessarily, or the very lowest, but in the neighborhood where they're at, it's the lowest point. So in this section here, this is the lowest point in that neighborhood. Here, this is the highest point in that neighborhood. I want you to also start thinking about the values of the derivative around these points. We calculate those by putting tangent lines. At those special points, the tangent lines are actually equal to 0. They have a slope of 0. So every single place where we had a maximum or a minimum in the neighborhood, the slope of the tangent line was equal to 0. Now let's get some special names for these. Anytime you have that neighborhood maximum or minimum, we refer to those as relative or local extrema. So up here at the top, we have a relative or local maximum. Here's another relative or local maximum. And finally, a relative or local minimum in this picture. The extreme value theorem actually talks about the very highest point and the very lowest point. So we have some new names. I'm going to change this one up here at the top, this point right here, and give it a new name. I'm going to call that the absolute max. It is the very, very highest point on the entire graph in that curve from A to B. Same thing with this point down here below. It's the absolute minimum. It just so happens that it actually occurs on the endpoint. Our job today in this section is trying to figure out where all these places are. Where are the relative local maxes and mins? Where are the absolute maxes and mins? And to do that, we're going to make use of the fact that every one of these potential places in between A and B that have horizontal tangent lines are going to have to be considered. Okay, these potential places have a name. They're called critical numbers. They occur anytime f prime of c is equal to 0, or places where f prime is not differentiable. So you can see over here that would mean like a sharp turn and of course like a peak or a valley. So those horizontal tangent lines and undefines will tell us all the potential places where maxes and mins could potentially occur. Here's some quick guidelines. You don't need to jot these down. These are just the guidelines we're going to go through when actually going through an example. We're going to find the critical numbers first, evaluate f at each one of these, evaluate the endpoints just to see if they potentially could be higher or lower, and then pick out which one's the minimum and which one's the maximum. So let's look at an example on how you go through this process. Okay, so I'm going to find the extrema of f of x equals 3x to the fourth minus 4x cubed. The interval it's on is -1 to 2. So I'm going to start with the derivative. So f prime equals 12x cubed minus 12x squared. To find the critical points, you set this equal to 0. And now solve by factoring. Looks like these have a 12x squared in common. So I have x equals 0 and x equals 1. These are the critical points. Next thing I need to do is actually evaluate their y-coordinate. Find out how high or low they are. So I'll start with f of 0. I'm substituting these numbers back into the original function, just looking for a y-coordinate. That one would be 0. When I substitute 1 in there, I get -1. Next, we're not done yet. I still need to check the endpoints. Again, they could potentially be higher or lower than these numbers. So I'm going to check -1, which gives me 7, and also 2. That's 16. From this list, now I can actually find out which one's biggest and which one's smallest. 16 is the biggest, so this is the absolute max. -1 is the smallest, so it's the absolute min. The other numbers, they must be really important. It's just at this point in time, we don't know why. We'll learn that later on in other sections coming up very soon. Just to confirm that everything we found is correct, use your paper that you're taking notes and compare it to this graph. Here are the values that we actually talked about. And you can see everything seems to be matching. 0, 0, it's definitely an important point, just we don't know what it's called yet. It looks like a local max. 1, -1 is the absolute min we found. -1, 7 is an endpoint, just not really significant. And finally, 216 is the absolute max. It was the highest point on this graph. Everything seems to be confirmed with what we found. All right, let's look at another one. In this one, I'm trying to find the critical points first so I know where to begin. So I'll start with the derivative. 2 minus 2x to the 1/3, -1/3. I'm going to go ahead and write that with a non-negative exponent. So the x to the 1/3 goes to the bottom. Already I have a critical point. Since there's a fraction, that x value is producing an undefined value. When x equals 0, I know that this derivative is undefined, so it's going to be a critical point. I'm going to go ahead and stick this over here just so I remember to check it. So it must be something like a sharp turn, something like that that's causing that. All right, next, I have to solve this. This takes a little bit of algebra work. I'm going to go ahead and move over the 2 over x to the 1/3. Multiply both sides by x to the 1/3. Divide by 2. then I need to undo x to the 1/3. Just cube both sides. 1 cubed is 1. So I have two different critical points, just for different reasons. F of 0 comes from an undefined. F of 1 comes from an actually setting it equal to 0. So they'll look different on the graph. The first one will be a sharp turn, the other one will be a smooth curve. Now, we can't forget to check the other ones. The endpoints could potentially be higher or lower. F of 0 is not too bad to find. All the x's are 0, so that's just 0. 1 isn't bad either. When you plug in 1, 1 to any power is 1. So that's 2 minus 3, or -1. Let me jump down to f of 3. F of 3 requires a calculator. You can't do it by hand. So I went ahead and did that, and that's -0.24. Going back to f to -1, I think it's worth actually taking a look at how you evaluate this. So 2 times -1 minus 3 times -1 to the 2/3. Order of operations says you have to do the exponent first. So I need to figure out what -1 to the 2/3 power would equal. To do that, I'll just go ahead and translate it back into a root. I have -3 times -1 squared. Cube root of 3 times -1 squared. All right, so that will be the cube root of +1, or 1. This one turns out to be -5. So here, my lowest value is -5. My biggest value is 0. And there's my absolute max and min. Now, remember, keep your note sheet out. I'm going to go ahead and show you the picture of this so you kind of can compare with what we just found. Here's the graph. No surprise there at 0, 0 that we had a sharp turn. That's where the derivative was undefined. So it's good we put that in there. It's definitely important. The other important value is an endpoint in this case, -1, -5. It's the very lowest on this curve. 1, -1, certainly important. We just don't know why yet. Looks like a relative min. And finally, 3, comma, -0.24. That's another endpoint. So we had to check it just to make sure. Okay, we'll go ahead and try some of these tomorrow, finding critical points and locating absolute maxes and mins. Remember, it's all according to the extreme value theorem. We're guaranteed to have an answer for both max and min because of that theorem.